We know a lot about the angular momentum operators simply because they're the generators of rotation. And we showed that the orbital angular momentum, L equals r cross p, is a perfectly valid angular momentum for a scalar wave function, a wave function with a single component defined over all space. And because the Hamiltonian for a particle in central potential commutes with the orbital angular momentum, then they share the same eigenstates. These eigenstates are called the spherical harmonics, and they're characterized by two quantum numbers, an L and an M. L is related to the magnitude of the total orbital angular momentum, and the M is related to the projection in the z direction. Now, interestingly, these two numbers are both quantized. Classically, if you have an angular momentum vector, it can have any direction and any magnitude. Quantum mechanically, we can see that the angular momentum must have individual quanta, so it has particular lengths that it can be. Even more interestingly, if you measure it along a particular axis, say the z-axis, you'd normally expect that the magnitude of that measurement will depend on the angle between the vector that you're measuring and the axis. But in fact, if we look at the z component, we can see that the values are always going to be quantized. So we'll always get particular values. And indeed, no matter what L is, we'll always have an odd number because there are two L plus 1 projections, two L plus 1 values for M. Now, this quantization of angular momentum is a fairly dramatic prediction, and so of course the experiment was done. The first experiment was done by Stern and Gerlach. And they measured the magnetic moment of silver atoms, which for charged particles is proportional to the angular momentum. And they did indeed discover that it was quantized. But they found something odd, which is instead of getting an odd number of peaks, they found an even number of peaks. And having an even number of peaks was odd, because of course they expected an odd number of peaks. This caused a large number of clever, reasonable, and entirely incorrect explanations to be put forward, but in the end there was only one conclusion that survived, that the valence electron of the silver atom must have some kind of intrinsic angular momentum, and this angular momentum was called spin. And the spin didn't look anything like an orbital angular momentum, because this value that it had for an electron was always a half, which isn't even an allowed value for orbital angular momentum. It never changed, so this ms value was therefore always either plus a half or minus a half. And so the real Hilbert space for an electron was not as simple as a single component scalar field. It actually has two components, a spin up and a spin down. And this also helped explain why in the Pauli exclusion principle, two electrons could be in any given state of the spatial wave function. Now, the operators corresponding to the three components of angular momentum for spin must have the right commutation relations, these commutation relations up here, and because they're so simple, because the dimension of the Hilbert space is just 2, we can write them down directly as matrices. And these matrices are proportional to something called the Pauli matrices. And the Pauli matrices are, and if we write them in the eigenstates of the spin in the z direction, then obviously the z1 must be diagonal, and it's just 1 and minus 1 for the two eigenvalues, because the spin operator is just going to be h bar on 2 times the Pauli matrices. Okay, so the z1 is just simple directly because we're working in the eigenstates of this operator. And then the x and y are given like this. And as you'd expect, those observables are all Hermitian. If we measure the spin in the direction n, where n is a unit vector, then the observable for that is n dot s. If we were to rotate this system, then the transformation would look like this. If we rotate it around the axis n, an angle theta. In actual fact, this rotation here only works on the Hilbert space defined by this 2x2 system. So this is just a 2x2 matrix, and so it's acting on this 2x2 system, the spin up, spin down. In fact, if you had a spatially distributed system, like an electron, it would have a wave function over all space. In fact, it would have two wave functions over all space. So it has kind of two dimensions to its Hilbert space. Then, in fact, the rotation would be the total angular momentum, and the total angular momentum would be the sum of the orbital angular momentum and the spin angular momentum. So this is for the whole systems. That would be, say, the spin version, and this would be the total rotation. Now, if we rotate our system around 2 pi, an angle of 2 pi, in other words, a 360-degree angle, you'd expect all your measurements will be exactly the same. You don't expect that to change the universe in any way. In terms of the states, that means we don't exactly have to have exactly the same state, but we have to have the same state up to a phase. And you might expect to have the same state completely, but in fact for these spin half systems you can show that isn't true. Let's try rotating just a spin half system, ignoring the spatial degrees of freedom for the moment. Just look at the spin degrees of freedom. Let's imagine we rotate them through an angle of 2 pi. Then we've got the spin rotation, and we'll rotate in the z direction. So that would be the k unit vector through an angle of 2 pi. What, you might ask, is this matrix exponential? Well, you can define it by the power series expansion as normal. And for a general matrix, it's probably easiest just to type that into something like Mathematica to get the answer. But in order to calculate it yourself, actually the easy one to do are the diagonal ones. The exponential of a diagonal matrix is just the exponentials of the various diagonal elements, which is fairly easy to prove. And so this, if we do that, we end up with almost the identity, but not quite the identity. It's the identity up to this minus sign. So if you rotate a spin half system around 2 pi radians, then you get the same state back, but with a minus sign. That minus sign doesn't change anything if you're only looking at that system. The only way that minus sign could affect things is if you were looking at two systems and you're looking for interference between the two. And indeed, that interference has been seen using neutron interferometry.